In this video, what I want to do is illustrate the calculation, the determination of entropy production for systems that are operating in a cycle. And so remember that a cycle is a very special example of a closed system process. So let's have a look and see what we've got. There's two things we're going to talk about. A system operating in a cycle when it goes through one single cycle. And then we're going to also talk about systems that are operating steadily in a steady state, steady flow manner in a cycle. And that has to do with equipment that we observe in our day in and day out lives. So first thing we're going to do is give you a little crash course about cycles, little reminder type crash course about cycles, and then worked out problems. Going to have a problem associated, a couple of problems associated with a system that undergoes one single cycle. And then talk a little bit about, say, real world observed equipment that operates steady as time goes by. There are systems that operate in a cycle continuously in a steady state manner. So here we go. Cycle reminder crash course. Closed system. So here's my depiction of a closed system. I like to just show a piston and a cylinder, heat transfer in, work out. And here's an example of a process. Just covered a video regarding entropy production of a process 1 to 2. See, it's a process. It goes from one state to another state. Things to on a PV diagram there. Delta U. Delta U, the change in internal energy might be positive, might be negative, might be zero. It all depends on the process. Same thing for delta S, the change in entropy. It might be a plus value, might be minus, it might be zero. Now let's look at that same closed system that's operating in a cycle. This little example problem I showed, it starts at state 1, goes to another state, another state, another state, another state, and back to 1. That's what completes the cycle. And so I hope this is enough of a review for you to remember, okay, on a PV diagram for this closed system, here's a clockwise rotation. I can visualize the net work produced by this cycle is the area inside this curve. Another thing to remember is that when you go through a cycle, you start at state 1 and go through a bunch of crazy things, but you end right back up at state 1. Do you see that delta U is 0? You start and end at the same point. So therefore, delta S, which is a property, that also equals 0. Delta U equals 0. Delta S of the closed system equals 0. All right, so now let's depict a closed system. That was of the piston and cylinder. But remember that piston and cylinder is going through a number of processes. And the way we depict this from the engineering standpoint is, well, the example problem was a power cycle. It was making net power. And so the piston and cylinder and all its processes would fit inside this black box. And so to complete one cycle, you've got some heat added from TH, and you've got some heat rejected during another part of the process to TL. And as a result, you get W net out. Okay. Similarly, you could reverse the example, and here's our black box, and you can transfer heat from low to high. But that doesn't violate the second law as long as you realize it costs you some work, some net work to make that happen. And so visually, you can compare the difference between a power cycle and a refrigeration or heat pump cycle. Just look at the direction of the arrows on your sketch. That's why it's so important to start with a sketch. We can also write the first law for a system undergoing one cycle. So in the fancy way, the cyclic integral of del Q in equals the cyclic integral of del W out. Okay, got it? However, once we've got our sketch written and we look at our arrows, use a little common sense, we can say that a statement of the first law for either of these is QH minus QL equals W net by looking at the direction of the arrows. And then as a reminder, we've gone through one single cycle. So delta U is 0, delta S, entropy change is 0, delta any property is 0 because we're a closed system undergoing a cycle. Okay, that's your crash course on cycles. Now let's get into how do we define entropy production for a closed system undergoing one single cycle. So here we've got, this is not a 6, that's a Greek letter sigma, sigma cycle, sigma subcycle. All right, we're going to go back to chapter 6 and remember for a process, here is entropy production equals the entropy change. Well, it's going to be minus the integral of del Q over T integral across the system boundary. I love to rewrite this thing. So I flip the side of the equation to say the entropy production equals minus the integral of del Q over T plus the entropy change. Now, what did we just say about a system undergoing a cycle? For a cycle, delta S is 0. So we're getting a little more simplified for the entropy production of a closed system undergoing a cycle. Okay, and here it is. So now we're going all the way back to chapter 5. It says that the cyclic integral of del Q over T across the system boundary equals minus sigma for the cycle. And so I like to rewrite this. Sigma of the cycle equals negative cyclic integral of del Q over T. And I find this easier to work with as I'm solving engineering problems and homework problems. Sigma of the cycle equals negative cyclic integral of del Q over T across the system boundary. And then the statements of the second law says if sigma of the cycle is equal to 0, then it's just like a Carnot cycle. It's perfectly reversible, and it's possible. If sigma of the cycle is greater than 0, it's possible and it's irreversible. If sigma cycle is less than 0, numerically less than 0, that says your proposed process, your proposed cycle is impossible. It won't work. Okay, now worked out example for a system undergoing one single cycle. A gas is contained inside a piston and cylinder, and it's proposed to undergo one single cycle. Heat in the amount of 20 kilojoules is added from a high temperature heat source at 500 K. Net work in the amount of 6 kilojoules is proposed to be produced. Heat is to be rejected to a lower temperature heat sink at 300 K. Now that's enough to set up your sketch. Okay, so be comfortable with saying, okay, I've got to start with a sketch next because there's a lot of given information. I got to put that down on a sketch. Here's what you have to do. What is the amount of entropy production as a result of the proposed cycle? You need to come up with a number for that, entropy production in kilojoules per degree K. Is the proposed cycle possible or impossible? If it's possible, is the cycle reversible or is it irreversible? So here we go. We're going to start with the sketch. I like to show my piston and cylinder with the control surface in it. Okay, showing that it's a closed system. All right. The schematic is incredibly important. So here we've got, I've shown given information, and then I figured some other stuff out just as I was drawing the sketch. Given 2 temperature reservoirs, the high temperature 500, low temperature at 300. I drew that in. Given in the problem, 20 kilojoules of heat added during the cycle and 6 kilojoules proposed net work coming out. I'm drawing my sketch. I say, wait a minute. Visually, I can see what QL is going to be right now. It's going to be 20 minus 6. So I put it down on my sketch. I didn't wait to write things down. Statement of the first law, QL is QH minus W net. I looked at my arrows, 14. 20 coming in, 6 plus 14 going out. Now, what's the homework problem? It says, determine sigma for the cycle. I'll go back to my crash course. Okay, what is it? It's minus the cyclic integral of del Q over T across the system boundary. Here's my system boundary. I see two instances of heat transfer, one coming in and one leaving. So I've got two terms to worry about in my brackets and minus brackets. Let's worry about the heat transfer in first, plus Q in, QH divided by TH, del Q over T. What's going out? Well, it's a minus Q minus, it's going out, Q minus QL over T. Wow, okay. I got my sketch. I've got my expression for entropy production. I plug and chug. There's my numbers. I've got sigma cycle is plus 0.00667 kilojoules per degree K. That's greater than 0. Conclusion, the proposed cycle is possible. And since it's possible, it is irreversible. Not so bad. Do you see that? Do you see how you'd be sunk if you did not draw a sketch? You would be sunk on if you had the equation. Oh, what's my equation? What's my formula? Here's my formula. Okay. Now what do I do? You are sunk without a sketch. Next problem. A refrigerant is contained in a piston and cylinder, like R134A. It is proposed to undergo one single cycle. Heat in the amount of 22 kilojoules is removed, keyword, removed from a low temperature reservoir at 250 K. It's proposed that the cycle will require 8 kilojoules of net work to complete one cycle. Heat is rejected from the refrigerant to a high temperature reservoir at 320 K. A lot of given information, enough to answer the following. What is the amount of entropy production as a result of the proposed cycle? Now, it says it's proposed. Is it possible or impossible? If it's possible, is the cycle reversible or irreversible? We can answer this. All right. My piston and cylinder. Now, got to have the sketch. Let's see. Given information. It said 22 kilojoules was removed from the low temperature reservoir. Okay, I immediately put in the temperatures of my reservoirs, 320 and 250. Okay. Given 22. Also given, says it's proposed that we're going to use 8 kilojoules of net work to run this refrigerator. I can see with my eyes. I can see the first law with my eyes. I've got 22 kilojoules going in of heat, 8 kilojoules of work going in, negative work out. That's got to add up to 30. So I put 30. That's the first law. QH is QL plus W net. So do you see how that sketch can help you? All right. What are we trying to do? We're trying to calculate entropy production for the cycle. I go back to my crash course. I write down my formula. Formula. Now, I've got to tell you, I don't think I have this memorized in my head. I'd have to go back to the crash course too. But once I've got it written down, I can go to town now that I've got my sketch. Sigma cycle equals minus two terms, two instances of heat transfer. Let's work on the heat going in first, plus QL divided by TL. It's our integral. Then we'll worry about the heat rejected. So QH is a minus number, minus 30 over 320. Okay. Wow. Now I've got it. I got my numbers into my expression, plug and chug, being careful to keep that minus sign there. And I've got sigma of the cycle is plus 0.00575 kilojoules per degree K, greater than 0. Well, so this proposed refrigeration cycle is possible and it's irreversible. Not so bad. Okay, those are typical homework problems. Now we want to talk about entropy production rate for systems that are operating continuously in a cycle. And here's a couple of very often observed real-world pieces of equipment. Here's a refrigerator. Tends to run a lot, steadily. When it's running steadily. Here's a power plant. Power plants run 24/7, 365, okay, running steadily. Both of these are systems operating in a cycle. Okay, so the depiction, so here's the depiction of the power plant. Notice here, I've put dots over each of these energy transfer terms. Q dot H, W dot net, that's power, output power. Q dot L, that's the rate at which we're rejecting heat. Okay, sigma dot, that's okay. There's our entropy production rate. We've got a dot over top of that. Okay, and the same thing here on the refrigeration cycle. This is power needed to run the refrigerator. Okay, maybe a little repetition, but I think this slide is meant to drive it home. We just did two example problems for a closed system undergoing one single cycle. Here was our sketch. Here was our governing equation. Okay, notice it, no dot. Okay, and the units of our entropy production for the cycle were kilojoules per degree K. Now we're going to talk about some examples where our system is operating steadily. So we're interested in entropy production rate, sigma dot, for the cycle. So we're going to, whoops, my dot needs to move a little bit to the right here on my diagram, my slide. But the units for entropy production rate are going to be, well, kilojoules per second per degree K, or in other words, kilowatts. Kilojoule per second is a kilowatt. So the units for entropy production rate, kilowatts per degree K, is what we're going to work on next. Okay, determining the entropy production rate. Here's our governing equation, and this is actionable in terms of our little sketch that we're going to have. Is you see how the integral turns into the sum of all the heat transfers. In our case, for a traditional power plant or a traditional refrigerator, we've got two things to sum up, Q dot divided by T, and we've got two things to sum up. Okay, and the same drill. When sigma dot is greater than 0, the proposed cycle is possible and irreversible. When sigma dot, the rate of entropy production, is equal to 0 exactly, it's equivalent to a Carnot cycle operating continuously, possible and reversible. And then if we find sigma dot is less than 0, whatever's being proposed to you is impossible. All right, example problem. Now we've got an engineer claims to have invented a power plant which receives 150 kilowatts from a high temperature reservoir at 800 K and produces 100 kilowatts of net power, 150 kilowatts heat, 150 kilowatts net power. Now the inventor proposes to sell this to you. Inventor says, I want to sell this to you. Now I understand that you've got a nice river available, and so I want you to hook up what you're purchasing from me to the river heat sink. It's at 290 degrees K. Okay, so you're going to be rejecting heat from the power plant at 290 K. All right, so what I want you to do is say, all right, what's the entropy production rate for this proposed power plant using your heat sink? Then, is this proposed power plant possible or is it impossible? If it's possible, is the plant reversible or is it irreversible? So let's go and analyze this engineering inventor's claim and decide if we're going to buy this from him or her or not. Well, we'll start with a sketch. Here's our sketch. Okay. And so our sketch says, okay, here's our temperature limits, 800. 290 is our river heat sink. Okay, we'll put in what's given to us, 150 kilowatts of heat coming in, 100 kilowatts of net power coming out, and then simply by inspection, right? I'm going to apply the first law, 150 coming in, 100 going out. By observation, Q dot L must be 50 kilowatts by the first law. Okay, drop down back, we'll review our crash course. Sigma dot of the cycle is minus the sum of the Q dot over T's, and we see two of them. Okay, so minus, so we got two things in the brackets. you see the repetition coming in here. Let's work on the heat inflow first. 150 Q, TH is 800. There it is. Second bracket term, heat is leaving. So negative Q dot L divided by TL, negative 50 over 290. Plug and chug. Get on your calculator. Do the work. Don't overlook that minus sign. And you get sigma dot for the cycle is negative 0.01509 kilowatts per degree K. Uh-oh, that's a yellow flag. And you immediately say, not only is that a yellow flag, it's a red flag. And your conclusion is this proposed process cycle is impossible. And that's just it. And so you'd be very foolish to purchase this proposed power plant from this inventor engineer. Here's an alternative solution to the same problem. I just redrew my given information. And if I were not asked to find the entropy production rate, let's say that you're on your own, you're running your own business, nobody's asking you to find the entropy production rate, but you do want to determine if it's possible or impossible before spending your money on a proposed power plant. And so an alternative solution is to compare the claimed thermal efficiency of the inventor's proposed plant to a Carnot cycle efficiency. You're expert at this. I'll dust off my sketch. The Carnot efficiency, I've got this committed to memory. Energy sought over the energy that costs. For the Carnot cycle, heat transfer is linearly proportional with temperature. So I've got TH minus TL over TH. Got that in my head, right? And so I plug and chug. So for the given temperature limits, a Carnot efficiency would have the maximum possible thermal efficiency is 63.75%, 64%, maximum possible thermal efficiency. And the inventor's coming to you in 100 over 150. The energy sought, W.net, energy that costs, QH, is 67%. No matter how much you wish or hope, the proposed plant is impossible. You would be wasting your money. You'd be wasting your money in purchasing this proposed power plant because it will not work. Okay. So the claimed thermal efficiency is greater than the maximum possible thermal efficiency. I would dismiss this out of hand, and I'd tell that engineering inventor to go back to the drawing board, and you might want to reinvent and come back to me with a more realistic proposal, and then we'll talk. Example problem 4, a residential heat pump. Residential heat pump operates with a coefficient of performance, a COP of 5. The heat pump provides heat to the living space at a steady rate of 4 kilowatts. 4 kilowatts of heat is being added inside the house that needs to be heated. The living space is maintained at a temperature of 300 K, and the outside surroundings stay at a constant temperature outside the building of 283 degrees K. That sounds a lot like 10 degrees C, doesn't it? Okay. Question is, what's the entropy production rate for this heat pump? Entropy production rate for this heat pump. All right, let's see what we've got. We're going to draw our sketch, and let's see what was given. What was given was 4 kilowatts of heat is flowing into this room at 300 K. Heat is being transferred from outside at 283. We were given neither the net power needed to run it, nor were we given the heat flowing out of the surroundings. But we were given the coefficient of performance of the heat pump of 5. Okay, so let's see. That's energy sought over the energy that costs. Energy sought over energy that costs. We're seeking to heat our room, our house. What costs us is the electric power required to drive the heat pump. And so we can solve flat out, almost by eye, that the net power required is 4/5 of a kilowatt, or 0.8 kilowatts. once we've got that, just by eye, by inspection, we see that, well, I've got 4 going out and I've got 0.8 going in. So what must be going in here as Q dot L must be 3.2 kilowatts. So I put it on my sketch. I don't even go through the homework problem step by step by step. I kind of explain it here, first law, and the definition of coefficient of performance. All right, back to my governing equation. Might not have this memorized. Okay, well, I'll go back to either a formula sheet or back to some notes. Okay, sigma dot of the cycle is minus the sum of the Q dots over T. Okay, same old drill. What I like to do is start with the heat addeds first, so minus 2 bracket terms plus Q dot L over TL. I've got those numbers now. What's leaving? Minus Q dot H over TH. I've got those numbers, okay? Turn the crank, okay? So sigma dot of the cycle, once I do all my math, remembering that my pesky minus sign, sigma dot of the cycle is plus 0.002026 kilowatts per degree K. Got it. This is what was described is absolutely possible, and it's irreversible. Heat pump with a coefficient of performance of 5 operating under these temperature limits. Perfectly possible, but irreversible. Here's an alternative solution if you're simply testing to see if the heat pump were proposed and possible or impossible. If you were not asked to find the entropy production rate. Again, the same drill is I'd calculate the Carnot efficiency, energy sought over the energy that costs here. Well, let's see, the energy sought is Q dot H, so it's proportional to TH. And energy that costs, that's Q dot H minus Q dot L or W dot net. So we're going to just plug and chug. The Carnot coefficient of performance for the heat pump, gamma is 17.6. Wow. And the claimed coefficient of performance is 5. And so, yeah, absolutely, this is possible, and it's irreversible. So those were 2 specific examples of closed systems operating at a rate commonly found in everyday lives. So just to recap the examples, can you explain the difference between entropy production and entropy production rate? One had to do with a closed system undergoing one single cycle. Entropy production rate would be for equipment that's operating steadily. Okay, and so can you determine sigma for the closed system undergoing one cycle? Similarly, can you determine sigma dot, the rate of entropy production for a system operating at a steady rate? I hope those examples have helped you get ready to do homework problems that might be that simple, and some might be more complex. So anyway, I do hope that those examples have helped your understanding of entropy production and entropy production rate.